And a very, very special evening it is, where we get to celebrate some of our top mathematicians that have interacted with the maths competition over the last year or so. The Wits maths department is hugely into outreach and encouraging young mathematicians, particularly in competition maths, which is its own sort of a thing. But certainly it brings maths alive for a lot of these guys who and girls who would otherwise be enjoying their maths syllabus, but not be extended nearly to the extent that they are, thanks to the dedicated work that is done by the Wits maths department. And I would like to specifically welcome right up the organizer today, Jonathan Karev, who does such a lot of really, really good work with the competition and with training young mathematicians up. And I know that he follows their future very, very, very thoughtfully. John, I see that you're on the screen with us. Welcome, and thank you very much for the work you do.
Thanks, Simon. So now it's time to move on to Prof. Chetty, who will give us opening remarks.
Sure. Let me just introduce Prof. Chetty quickly for everyone who is not aware. He is the Dean of Maths. In fact, let me get his... he's the Dean of Science, the Dean of Science at Wits University, Prof. Nithya Chetty. And he is... does a lot of work on 2D materials and was the first to demonstrate that graphene is the hardest material known to humans. He's the Deputy Chief Executive Officer of the National Research Foundation, the NRF, which is the organization that funds so much research in the country. And a lot of you young mathematicians, as you move up the ranks into research posts, you will get to know the NRF very, very well, because they are the guys who could well be funding your salary in the future. He oversees the astronomy portfolio. He was overseeing the astronomy portfolio during the building phase of the Meerkat radio telescope as well. Is a very, very strong advocate of academic freedom and the importance of maintaining an intellectually free environment at our universities. So it is my great joy to welcome Prof. Chetty, whom I'm hoping is going to be on our screen in any moment now. There he is.
Thank you. Thank you so much indeed, Simon. Much appreciated. It's really quite a pleasure to be here at this very prestigious awards function for the Wits Maths competition. So a lot of effort has gone into establishing this as a very credible competition. It started off some years ago, 2018, I believe, by a small group of individuals. Jonathan's been very key right from the outset, but in the early days then, Professor Musamanzi, I want to recognize him, Professor Betsy Young, Dr. Celeste Johnson. So you would see that the individuals really come from disparate backgrounds, and that's very key, because everybody has come together to understand the importance of mathematics in this as a basis really for advancement in society. So the ideas around the maths competition really grew out of the need to develop an Olympiad community here in Gauteng. That was the basis for barely 4 years ago. But today, you will note, Simon, that 9 countries are now represented, which is really quite phenomenal, I think, in such a short space of time. And those countries, very quickly, aside from South Africa, these include Botswana, Cameroon, Kenya, Mozambique, Nigeria, Rwanda, and Swaziland. So I'm absolutely confident that this competition is set to grow within the context of Africa in the coming years. The total number of participants for the past year, over the course of this year, in this competition has exceeded 7,000, which I think is quite phenomenal. So to the winners of this competition, I do want to extend my hearty congratulations. I really want to commend you for taking this step forward and for getting involved in the competition. And I really want to express my appreciation to the the teachers that have encouraged the learners to get involved in all of their help and support, including at home, that makes this the success that it is. Now, why is this important? I'd like to start the argument from the issues that face all of humanity. We really are in the, as we go deep into the 21st century, plagued with a number of very serious problems. And this does not just simply pertain to us in South Africa or Africa. These are worldwide problems. For example, securing our energy needs, or paying more attention to the sustainability of our environment, and of course, climate change is a direct consequence of our rather reckless approach to the ways in which we've lived on planet Earth, particularly over the past 100 years. This requires then, in trying to address these problems that are going to be very vexed matters that are going to confront our future generations for many decades to come, we need a quantitative understanding of the problems that we face, not just simply waving hands or speculating or political argument, or being subjective about the issues that we experience and will increasingly experience over the years to come, not being emotional, but basing our arguments on the hard truth, on evidence-based arguments for the understanding of the world in which we reside in, but also impacting then on the policies that need to be made to mitigate against the circumstances that we find ourselves in. I do want to stress that whilst we live here in Africa and often find ourselves quite challenged by the difficulties that we experience, but the problems that I speak of are of a worldwide nature, does require a very broad multidisciplinary approach. So what then is the basis for a quantitative study of any sort? Clearly it is mathematics. It has to be, and the fact that we are floundering here in South Africa in dealing with some of the most basic fundamental aspects of society, for example, the security of our energy. Keep in mind that South Africa ranks amongst the top 10 producers of high-grade coal, and the technology around energy generation is more than 100 years old. So we should really be at the top of our game in terms of providing a secure source of energy, but yet we're anything but that. And what is the basis of that? It's us not having a community of people in society, in government, in commerce, in industry, that has a proper technical quantitative understanding of problems. You can only politicize so much, and like I say, only wave your hands so much, and the problems don't go away until you have a very quantitative understanding of the problems. And many of these the challenges are compounded by the fact that when you measure particular attributes that you're interested in, there often are fluctuations. So it's not that you measure the temperature every single day and you have the same temperature, it rises by some incremental amount over a consistent period of time, and then you conclude that there's global warming. No, there are fluctuations on various different timescales, and so you've got to invoke a statistical argument as to what the numbers mean, and make decisions that impact very profoundly on the ways in which we live our lives. So the statistical interpretation of the data that we accumulate is also an important part of this discussion. Clearly, we have a dearth of good quality students. We have a dearth of good quality teachers, mathematically literate teachers, and so long as we continue to have this deficiency in our schooling system, we will continue to have the types of problems that we are experiencing on a macro level within society. So I'm very adamant that we need to sustain our university systems, particularly our mathematics programs. I, as Dean of Science at Wits University, strongly advocate for aspiring for the highest levels of the various different disciplines within the mathematical sciences, especially in pure mathematics, but also in applied mathematics, computer science, statistics, actuarial sciences as well, theoretical physics. All of these are part of the mathematical sciences. So we've got to aspire for the highest levels of international scholarship, but maintaining these very high levels of academia within our university systems. We then have a basis to teach the next generation of teachers and the next generation of students. But all of this simply falls apart if we don't have a strong pipeline of students into our mathematical programs at our universities. And this is where the Wits Maths competition comes through very strongly. And I do want to commend the organizers for the vision that they've had already a few years ago, and long may that continue. I see the Wits Maths competition as contributing to popularizing mathematics, making mathematics more accessible, putting the fun back into mathematics, getting folk to understand the importance of mathematics, not just simply from a disciplinary point of view, from an academic point of view, but from a societal point of view. And I do want to see us growing this cohort into the future. I'm very proud to say that the Faculty of Science is a strong supporter of the Wits Maths competition. So I want to see us grow in this endeavor, and please count on my fullest support as Dean of Science. All I see on the call there, quite a wide range of academics from the Faculty of Science, once again drawn from different disciplines, and that is very revealing. It shows that there's great concerns crossing many other disciplines about the future well-being of the discipline of mathematics. It is the basis upon which we all pursue our quantitative studies and ultimately quantitative understanding of the world in which we live. Now, the competition, as I understand it, has 5 divisions. We have the middle primary grades 4 to 5, upper primary grades 6 to 7, junior secondary 8 to 9, senior secondary 10 to 12. And of course, we also include our undergraduate students, the first 3 years of tertiary education. So schools and universities then enter the competition. There are several rounds, as I recall. The first round at school, and of course, COVID kind of set us back a little bit. But my hope, Jonathan, is that we're going to get back to a situation where we can have more of these face-to-face engagements. But I can see with the large numbers involved, we want to have the initial rounds as being online. Top performers then are invited to the next round. And in 2019, that was held at Wits, but the last couple of years, this has been done online. But I think we should strive to get back to a in-person mode in the coming years. So there are lots and lots of people to thank for the success of this, and it's my pleasure then just to mention just some of them that have been brought to my attention. So the regional coordinators, Matthews Masola from Botswana, Linda Emery from the Eastern Cape, Elsie Shumbi from the Free State, and also representing the Northern Cape, Graham Evans from KwaZulu-Natal, Andrew Obus from Liberia, all the way from the West Africa. Welcome, Andrew. Ibrahim Simsek from Limpopo, Daniel Akintoye from Nigeria, also long distance away, but connected very ably through the network today. Jessica Weerbracht from Rwanda, for Labuschagne from the Western Cape. Am I still connected? Simon, am I still connected? Jonathan, am I still connected?
Yes, Nithya, you are definitely still connected.
Thank you very much. I'm having power issues here in my office at Wits. There's a nasty electrical storm outside, but just another minute and I'll be done. So colleagues, I want to recognize the regional coordinators and appreciate all of that. The papers, then the exam papers, and obviously developing questions that are exciting requires a lot of thought and planning. So I do want to recognize a number of colleagues that have contributed in this important way. The notable colleagues are Clint van Alten, Graham Evans, Ilana Flom, Jeref Fluxman, Callan Kotsen for Labuschagne, Dylan Nelson, Malwande Nkonyane, Jacques Duplessis, Evan Sneeman, Jacqueline Fenter, and Professor Betsy Young. Thank you, colleagues, for the dedication that you put into this competition that has resulted in the success that it is. The computer engineering team also plays an extremely important part in lending support to these efforts. And in here, I want to acknowledge Dr. Pravesh Ranchod, also Carl Ginster. They maintain the system and organize the streaming for this prize-giving event, which is quite an effort. So with that, Simon, my time's up. I really want to say that this is really quite a pleasure to do, and please call on my support. I'm very proud to be associated with the Wits Maths competition. I congratulate all the winners once again, and I wish you all the very best for a successful evening of awards. Thank you now.
Thank you very much, Prof. That was Prof. Nithya Chetty, the Dean of Science here at Wits University. And thank you so much for your support. I think you are quite right that the mathematicians are the lifeblood and the underpinning of so much of the other applied science that is done around the world and sort of through the university. And looking after our mathematicians is so absolutely vital at all of our tertiary institutions. It is now my great pleasure to call on Talitha Moore, who is here representing Sharp South Africa. They are the sponsors of the Wits Maths competition. I must tell you that John and I had an opportunity to donate one of her calculators. I don't think she was aware, actually. It was a spare one that John had to a youngster who's putting himself through A-levels, and access to that calculator made a huge difference to his ability to be able to self-teach himself the maths syllabus. So it is with great pleasure that we invite Talitha up onto the stage, as it were, the virtual stage. We'll just wait for her to be added to the broadcast. In fact, it is going to be John for a while. Is Talitha around, John? John, your mic is off.
Sorry, I think Tal's a little bit late, so I think let's start with Prof. Mossel.
Okay, fantastic. So we'll move on down the to Prof. Mossel, who is going to be our international speaker. It's Prof. Elchanan Mossel from MIT, the Massachusetts Institute of Technology, and is Prof with us? There he is. Prof, without too much further ado, I notice you've got a very carefully placed blackboard behind you. It's good to see the retro skills still with us. Prof, Prof, over to you.
Good evening, everyone, and I followed the ceremony from the beginning, and I want to start by congratulating everybody who participated in the competition, and congratulating all the winners for your achievements and for doing math. I want to echo some of what the others have said before. I think math connects to many of the sciences and many of the challenges that sciences can face or is facing in the coming years, and I will try to give you a glimpse of some of the mathematics that I'm actually doing. So I'm going to try to do something very ambitious for this audience. I'm actually going to use the same slides. Well, I'm going to try to use the same slides if I'm able to present them that I used in a talk that I gave in the International Congress of Mathematics this summer. Of course, I won't go over all the slides, and I'll just try to explain to you some of the connections between different areas of science and mathematics and the mathematics I'm doing, just to give you a flavor of what mathematicians are doing, research mathematicians are doing, and the connections to problems. So I've never used this software before, so it's all based on the assumption that I'd be able to present. So let me try to do that. So let me try to slides from my computer. And I'm going to upload the file. So sorry, it's the first time I'm using this software, so bear with me. And if not, I'm going to tell you some stories Wait to So it says that it's processing the slides. There are many slides, so maybe I should have done something. Okay, can you see my slides? Can I get some indication? I can't hear anybody. Can you tell me if you see my slides?
Yes, we can.
Hi, Prof.
Okay.
Yes.
So I'm going to talk about a very simple. I mean, I'm going to skip some of the slides. I'm going to tell you about a very simple process that I and fellow mathematicians like. This is a process that's drawn on what we mathematicians call trees. So what we call trees are different than what the trees that you see in nature, even in the southern hemisphere. Our trees are rooted on the top; they're not rooted at the bottom, so they're rooted over here. And I'm going to tell you about a process that lives on this tree. So this is the kind of processes that we study. I study probability. This is the kind of processes that we study in probability. Okay, so I'm going to give you an example. So in the example, I'm going to imagine and I'm going to toss an imaginary coin now, and this imaginary coin is going to tell me that I'm going to color the root of the tree by one of Q colors, 1 up to Q, in this case 2 colors, red and blue, so I'm going to color it red. So this is not so interesting. I'm just tossing a coin. What's going to be a little more interesting is what's going to happen next. I'm going to have this process of repeatedly copying from the parent to the child, except that sometimes I make mistakes. So here's the way I'm thinking about it. I'm going to toss a coin. This is now not going to be a fair coin. It's going to be a coin. In probability, we like coins that sometimes are unfair. That's going to land hand with probability some number theta, and going to land with probability 1 minus theta is going to land tails. So if it lands head, I'm going to copy, and otherwise I'm going to toss another coin, my fair coin, and this is going to tell me if I'm red or blue. Okay, so basically what I'm doing, I'm copying with errors from my parents. So I do it over and over again, like this, and I keep doing this. So this talk again was intended originally, or the slide were intended for general audience, but we are going to mostly talk about DRE trees. So DRE trees are trees where every node has D children. So this is not a DRE tree, right? Here, this node is 1, 2, 3, 4 children, and this node is only 1 child. But we are going mostly to talk about DRE tree, especially in what I'm going to talk about. So let me try to give you some connections to the sciences. So maybe you'd be surprised. Don't worry about the equations here. These are equations that people in the area of what's called statistical physics. I mean, your dean obviously knows a lot of statistical physics. This is a model that was actually invented in statistical physics when people were trying to understand magnetic properties of material. So you should think maybe about blue and red as plus magnetization or minus magnetization, right? We all know that batteries have a plus side or a minus side. That has to do with the magnetic properties or the electrical properties of batteries. And when we study materials, as did the Nobel laureate in physics Hans Bethe, we try to understand the magnetic properties of materials, and it's hard to do. And one of the models that he came up with is exactly the model that I described before, and indeed in physics, this is called the Ising model on the beta lattice, right? So don't worry about the equation. This is how physicists try this model. It's a very simple model. And as you see, this is the original paper where it was invented. It's almost 100-year-old model. Okay, so this model actually came from physics, even though I explained it in a very simple way. I just how I toss the coins and the propagation of the color from the roots through the tree. This was a simple but useful approximation for magnetic properties of materials. So I'm just going to give you a hint about the mathematics that comes into this, and of course I won't do all the math, but I'll tell you, this is results. We were in 1935. Now we're talking about the 1960s. Harry Kesten was a very famous mathematician who did a lot of work in probability. He escaped the Holocaust in the Netherlands and moved to the US and has contributed a lot to probability. And Stigum was his student at the time, and they wrote this very influential paper. And I won't tell you too much about the paper. I'll just tell you what the statistical picture that you see. And what they saw is that they saw there's two kind of behaviors. There's a behavior that I'll call subcritical. I don't know if many of you have seen this bell curve. These bell curves look like the Gaussian distribution or the normal distribution. And sometimes you have a behavior like that where you see this bimodal distribution or bimodal graph. And Keston and Stigum already in the 1970s, in the 1960s, were able to understand when this happened. So again, I'm going to show you a slide with a lot of information, but I just want you to pick one line maybe from this information. And this is what's written here in this line. I hope that you can see my pointer. So there's two important parameters from the model at the point of view of the Keston and Stigum. One is D, how many times do you duplicate? How many children that does each node have in the tree? How many branches that each branch branches to? That's this number D. And the number of data, which shows the fidelity of the process. How likely are we to copy versus to have an error or to randomize, right? So, and what they show is that really there's one important equation, which is no matter how many colors there are, there's one important equation which says, is it true that d theta square is bigger than 1 or less than 1? So again, if it's less than 1, we get this bell curve, this very famous picture that we get in statistics and probability, and it's used all the time. But if d theta square is bigger than 1, then we're getting something else. We're getting this bimodal picture. And in this bimodal picture, there's a signature of what was the original value on the root of the tree, right? You remember how I described the tree? I just started from one value, then it duplicated many times. And what they show is that if d theta square is less than 1, you lose this original information about the root. If d theta square is bigger than 1, you keep some of this information about the root. Okay, so I'll try, again, this is the picture again. This is the picture that you get if d theta square is less than 1. Okay, this is again from simulation. This is if d theta square is bigger than 1. And that they prove. Everything in mathematics is asymptotic as, the tree grows bigger and bigger and bigger and bigger. Okay, so that's kind of a picture of, the kind of probability that we're doing. It involves a process with randomness and repetition and errors, and we want to understand what's the structure of that. Like we said, this process came from physics, and I want to give you at least one more connections. I mean, to one of the other sciences. So I'm going to skip some slides here, and I'm going to connect it to the work of Darwin and to research in computational biology. So I know that many of you know the story, but I'm going to tell you the story briefly anyway. So there is the theory of evolution, and that Darwin is maybe one of the main figures behind advancing this theory or inventing this theory. And if you want to look at the picture, this is an old picture that's related to Darwin's work. And I want to first of all start from this is the geographic picture. This is the islands where Darwin, in one of his trips, was studying these finches. These are pictures of these finches. And after studying the geography of these islands, when these finches live, and studying the morphology of the finches, Darwin, in his notes that later were published as part of his famous book, drew this tree. So this tree looks very, very similar. Of course, it's not drawn by electronic software, but it looks quite similar to the tree that we've seen before. And the picture to have in mind is the picture that, Darwin was imagining that there is a species here that's extinct, and we don't know this species anymore. But then there was some bifurcation into multiple species that became different, maybe in Darwin's picture, because each was in a different geographic unit, maybe separated by different islands, or maybe separated by mountain chains. And it happened over and over again. And then he said, well, there's a lot of information that's missing here, but A is maybe this finch, and B is this finch, and C is this finch, and D is this finch. And Darwin conducted this investigation based on the morphology of the finches that he found, and based on the geography. He said that is the likely story of how how these finches evolved. And this story with the finches really played an important role in founding evolutionary biology. Now, what I want to tell you is that these days, the work of computational biologists or people who work in evolution is very different. It's very different because, they travel much less and they use math and computation much more. And the kind of work that they do, instead of using morphology like we did here, they use genetic information. So again, as most of you know, or all of you know, we have genetic data that dictates a lot of what we do. So a lot of us have a DNA. People have DNA, and you know, some other basic animals maybe have RNA. So, but they have DNA, and the DNA evolve. And what people in labs do these days, they collect DNA, maybe from birds or bacteria or some other species, and they collect these DNA sequences. They put them in a computer software, and they press a button, and the button says, "Oh, this is how they're related." Right? So what Darwin did by intuition or by understanding geography and so on and so forth. Now there's software that uses math in order to produce this what's called phylogenetic tree, or these trees that relate these different species. And doing so is very useful. You know, it's used, for example, in deciding what is going to be the flu vaccine, and you know, and it's used in many areas of both just understanding biology and also predicting what biology will do. Okay, so that's the picture, and I want to maybe show you just one or more slide and try to connect the two processes. So this is the picture that was made by one of my collaborators, Kostas Daskalakis. He later won the Nevanlina Prize partially for our work, and you know, this is sort of a cartoon of how the two processes are connected. So there was this broadcast process that I talked about before, and the evolutionary process. And what you should think about when you see this image you should think about it as an array of many pixels. Each of them is black or white. So, you know, they have this array of many pixels. And there's the broadcast process that we've seen at the beginning, and the broadcast process that for each pixel separately or independently, we have this process of copying the pixel or otherwise randomize it. So of course, when we do it, we get a more and more blurred picture of this image, which is supposed to represent the DNA, the DNA sequence of the species. And at the end, we have all of this blurry pictures that you see in the bottom. Now, what we talked at the beginning is we talked about the goal of recovering this ancestral sequence from all of these images. The problem in phylogeny, or the problem that Darwin studied, is a little different. What Darwin studies, or what people in evolutionary biology study, they study a problem. I'm giving all of these images, but they are not ordered in this way. I don't know that this species and this species splitted recently. I'm giving it some random order. Somebody went to this island, or I don't know, you know, where you collect DNA sequences of dinosaurs. I don't know if they're accessible, but suppose we were. So somebody go to Jurassic Park and collect some DNA sequence. Somebody go to some other place and collect some DNA sequence, and they're all shuffled up. And you don't know that these two are relatives, or these two are relatives. You get all of these DNA sequences, and your goal is actually to recover the relationship. And you know, again, I won't try to tell you too much about the history, but this model was introduced in about the same time in the 1970s by people, very, very prominent figures in statistics, by Jerzy Neyman, and very, very prominent people in biology, by Jukes and Cantor. And it's exactly the same model with some caveats that comes from biology that I won't talk about, but I'll just give you a flavor of the kind of math that I'm doing. So in the kind of math that I'm doing, you know, the same bound that we saw d theta square is bigger than 1 is fundamental for this problem of recovering these trees. So, you know, in particular in our work and works of other follow-up work with others, it was shown that if d theta square is bigger than 1, then you can recover these phylogenetic trees, these relationships very, very easily. And if d theta square is less than 1, you cannot do it, you need much more information, and it's a much harder problem. So I think I'll stop here. I'll just run through the slides to show you that, you know, this process is also related to problems in social networks. It's related to problems in number theory, to the non-backtracking random walk, to linear algebra, right? So that's the kind of work that we mathematicians are doing. You know, you see there's a lot of pictures that I'm not going to show you. I'm just going to say thank you. And I don't know if that there's time for questions, but if there is, I'm happy to take questions. Thank you.
Thank you very much, Prof. And most interesting. I think the only mechanism we have for questions, unfortunately, is through the comments on the on the YouTube channel, which is probably going to be a bit clunky. We maybe should have primed people to ask questions during the course of the the broadcast, and for that I do apologize. I also realized we didn't really introduce you properly. I was scrambling. I wasn't expecting to have you come straight away. So let me just let people know some of your background. You are at the moment part of the senior faculty at the MIT Maths Department. And then you've also got a joint appointment at the Statistics and Data Science Center of MIT's Institute for Data Systems and Society. Prolific scholar, more than 100 co-authors and over 150 papers. And Prof. Mossel also has advised 10 grad students who have subsequently held faculty positions all over North America, as well as at Chinese University of Hong Kong. He's a prolific award winner as well. Most recently, gave the special sectional lecture at the International Congress of Mathematics in 2022. So, Prof, we were very, very honored to have you with us, and we really, really do appreciate the time that you took out of your day to join us. Right. Well, the news is that Mrs. Talitha Moore hasn't been able to join us from Sharp, or not yet, anyway. So I do believe we're going to move on with the school and team awards. And the first one, the middle primary, is going to be presented. John, you might actually need to help me here, because we did discuss at the beginning whether we were going to change this possibly. Is this going to be Pravesh?
This is Pravesh, yes.
Okay. Right. So Pravesh will be presenting these. He's a senior lecturer at the School of Computer Science and Applied Mathematics at Wits, and a member of the Rail Lab. Pravesh, over to you.
Hey everyone, so I'm going to be presenting or announcing the winners of the middle primary competition. The first thing I want to mention is just the idea of quintiles, which exists in our school system. And what this concept models is the idea that we have a very varied landscape in terms of schools. We've got some schools that are very high resourced and some schools that are very low resourced. And we've taken the decision that in this competition we want to acknowledge the miracles that some of the schools in the lower quintiles are able to pull off. And so the school system has quintiles ranging from quintile 1, which is schools with the lowest resources, to quintile 5, which has the best resources. And we wanted to make sure that we properly acknowledge the amazing work that people are doing at all levels of available resources. So in the middle primary category, I'm going to start off by saying that we have Boitekong Primary, which is recognized as a notable quintile 2 school. We've got Chokwe Primary, also as a notable quintile 2 school. Yeshiva College, which achieved 10th place in Gauteng. St. Catherine's Convent, 9th place in Gauteng. King David Linksfield Primary School, 8th place in Gauteng. King David Santon Primary School, 7th place in Gauteng. King David Victory Park Primary School, 6th place in Gauteng. Law School Virda Park, 5th place in Gauteng and 10th place overall. Pinehurst Primary School, 9th place overall. Rustenburg Girls Junior, 8th place overall. Trinity House Rand Park Ridge, 4th place, Gauteng, and 7th place overall. Law School Tegerpoort, 3rd place, Gauteng, 6th overall. And Somerset House, 5th place overall. Moving on to Star College Durban, 4th place overall. Law School Hennops Park, 2nd place, Gauteng, 3rd place overall. I'm sure that's supposed to be Hennops Park. Sweet Valley Primary School, 2nd place overall. And our winning school in the middle primary category, we've got Red Hill Primary School, 1st place in Gauteng and 1st place overall. Back to you, Sam.
Excellent. Thank you very much. And a big congratulations to all of those schools. Absolutely fantastic to see them getting involved at such a young age with maths. We move on to upper primary. And this presentation is going to be provided by Roddy Martins, who's a lecturer in the Wits School of Mathematics, and he works primarily in graph theory. Just waiting on Prof. Roddy Martins.
Oh, there we go. Awesome. Thank you very much, Simon, and good evening to everybody. So I will be announcing the winners for the upper primary schools. So we have Boitekeng Primary School, which is a notable quintile 2 school. We have Mbazini Combined School, notable quintile 2 school. Then we have King David in Sandton, 10th place in Gauteng. Yeshiva College, 9th place in Gauteng. There we go. Trinity House, Preparatory Rand Park Ridge, 7th place in Gauteng and 10th place overall. Auckland Park Preparatory School, 6th place in Gauteng and 9th place overall. We have King David Victory Park Primary School, 5th place in Gauteng and 8th place overall. Then we have Laerskool Tygerpoort, 4th place in Gauteng, 7th place overall. Then Rustenburg Girls Junior School, 6th place overall. King David Linksfield Primary School, 3rd place in Gauteng, 5th place overall. Then Red Hill Primary School, 2nd place in Gauteng, 4th place overall. St. John's Preparatory School, 1st place in Gauteng, 3rd place overall. And then Somerset House, 2nd place overall. And Sweet Valley Primary School, 1st place overall. So congratulations to all of you guys that participated.
Thanks, Ronnie. I think we're sorry.
There I am.
Sorry.
Yeah, no, we're all good. Thanks. Yeah.
I think it's time for Talita's presentation. We should have Jacques presenting the Paul Laridan Award next.
Okay. So, but are you going to go to Talita first? Okay, fantastic. So let me very, very briefly introduce to you Talita Moore, who is from Sharp South Africa, who are the sponsors of this competition and to whom we are very, very grateful indeed. Talita, thank you very much for joining us with a youngster as well.
Thanks, guys, for having me. I really do appreciate it. Thanks, love. Yeah, sorry I was late. It's the youngsters' fault. We just want to say we're so excited by what you guys are doing for maths in South Africa and this amazing competition. And we really want to see where your youngsters go with regards to maths and everything. You know, I was at the Labour Centre this morning and nothing works, and it's very frustrating. And it's so nice to see youngsters who are working hard to solve problems, and that's what we need in South Africa. We need young, dedicated students who are going to solve problems and make South Africa better. And so that's why we're sponsoring here, and we at Sharp are really excited about everything that you guys are doing. So congratulations to all the winners, and enjoy your prizes. And remember that if you are in high school, you can visit our website, which is maths@sharp.co.za. We've got free maths worksheets that you can use. Maybe not for you guys who are the smarty pants, but share with your friends who need some help with maths as well. And for any of the teachers who are listening, we also have YouTube videos and a Facebook page as well. So if you are looking for any help with any questions, obviously not while you're writing exams, we'll definitely help you out there as well. So enjoy your evening. And again, well done, guys. We really celebrate everything that you guys, including these students and all the dedicated teachers who put in the time and effort to help their students here. So if any of the teachers are interested, we're happy to do workshops with them on the calculator. So you are welcome to get in touch. John has my number, so just you can WhatsApp me. I'll be back in the office from the 1st of December. So yeah, good night and enjoy the rest of the presentation. Thanks, guys.
Thank you so much, Talitha, and once again, just a huge thank you to Sharp South Africa for sponsoring this competition. We're going to move on to the junior secondary prize. This is the Paul Laridon Prize, and it is going to be presented by Jacques Duplessis, who was close to Paul Laridon. Jacques is a lecturer in the Wits School of Mathematics Education. The Wits School of Education, deputy head of school in charge of initial teacher education. His interest is across mathematics with a focus on the relational features and structure in mathematics, in particular algebraic reasoning and geometry. And he's part of the focus groups for the Council of Higher Education on Standards of Teacher Education, and he serves on the NECT focus group on classroom dynamics. Paul Laridon was his lecturer in an honours course in functions, and a colleague with whom he had the privilege to get to know on a personal level and share ideas with. So Jacques, thank you very, very much for joining us to present the Paul Laridon Prize.
Thank you very much, Simon. Much appreciated. Yeah, as you said, I was a colleague of Paul. I first met Paul when I did my honours at Wits. I got a bit bored of what I was doing mathematically, so I decided, okay, let me just go and try and do something more. So that's where I met Paul, an outstanding human being, a very friendly, softly spoken person that cared about mathematics and cared about the people that he surrounded him with. He was an outstanding mathematician, and his contribution to maths education in South Africa spans over 40 years. In his role as a maths educator at the university, Paul first taught the methodology and pre-service secondary mathematics teachers and developed programs at both a graduate and a postgraduate level. In 1990, Paul was a founding member of the Center for Research and Development in Maths and Science and Technology Education, shortly known as RADMAST. Under Paul's tireless direction, RADMAST research and development work in maths education expanded through all 9 provinces in South Africa. Paul's contribution to education in South Africa is characterized by its extent, its quality, and its utter commitment to create support for teachers across different contexts throughout the country. Every mathematics teacher and every scholar of mathematics in the school have come across the textbook series of classroom mathematics, which Paul, as a talented team, and his talented team of co-authors, under his leadership, excuse me, wrote many iterations of. In 2000, Paul became the first honorary member of the AMESA, the Association of Maths Education in South Africa, where he was honored for his lifetime commitment to excellence in the mathematics classroom. So Paul's dedication focused in the field of mathematics education, from classroom practice to national development and policy, was an inspiration to those of us who worked with him. He was a humble and kind man, and it is for that reason that we request his memory be honored in the Paul Laridon Awards that are made available in this esteemed competition. So yeah, I'm about to announce the winning schools in the junior secondary. Mbezeni Combined, Notable Quintile 2 School. Oh my goodness, I hope I'm going to pronounce these properly. So the Sise Lukukanya High School, Notable Quintile 2 School. Then the Tenjwe High School, Notable Quintile 3 School. Tabani High School, a Notable Quintile 3 School as well. St. Catherine's Convent, the 10th place in Gauteng. Then the Eduplex High School, 9th place in Gauteng. Curro Academic Parkdean, takes the 8th place for Gauteng. Acts House of Education, 7th place in Gauteng. Then well done to St. Stithians Boys College for the 6th place in Gauteng. Woodhill College takes up the 5th place. Yeshiva College, well done. You have the 4th place in Gauteng. And the GSN DBC Byumba, 10th place overall. Rondebosch Boys High School in 9th place overall. St. John's College takes up 3rd place in Gauteng and 8th place overall. Graceland International, 7th place overall. Then well done to King David High School, 2nd place in Gauteng and 6th overall. That's King David in Linksfield. The Star College in Durban, 5th place overall. Red Hill School, 4th place overall and 1st place in Gauteng. Herzliya High School, 3rd place overall. The Ambassadors College, OTA, 2nd place overall. And Welkin International School is our 1st place overall winner this year. The winning schools in the senior secondary. I think we've got a little bit of a glitch there. Well done to those junior schools for their performance in the competition. A well-deserved prize that the 1st place winners are going to get. Well done, folks. Okay, so the winning schools, then junior school secondary, Star College in Durban.
Okay, so we've lost Jacques. Apologies for that. So we are going to be. So that was the Paul Aridon Prize for junior secondary schools, and we're going to be moving on to the Peter Fridgen Prize for winning senior secondary schools. And this is going to be presented by the brother of the late Professor Peter Fridgen. Peter was from the School of Statistics and Actuarial Science, and Michael will say some words about his brother before making presentations.
Well, it's a great pleasure to be here this evening and to be joining you in an award that I think would be near and dear to the heart of my late brother. My brother Peter was an exceptional human being, an educator in the true and classical sense of the word, willing to engage with his students and always available to mentor them. Even at prep school, he was good at maths, but I don't think he originally envisaged mapping out a career in academia. When he finished his postgraduate degree at Lancaster, he returned to South Africa to teach at secondary schools, preferring to work with kids who came from underprivileged backgrounds and willing to inculcate in them a love for numbers, for the beauty and symmetry which comes from engaging with them, and the thrill of finding their hidden connections. He had a remarkable mind, both in terms of a prodigious memory, but also in terms of applying what he learned from maths to a wide range of fields in which he had either a hobby or academic interest. I constantly meet people who were from other faculties and who remember how he was able to help them to refine their research programs because he understood the applied mathematics, but also understood their subjects. I also meet former students who remember him for his gentle and thoughtful insights, which helped them to advance their studies. In that sense, he seems to have been an unusual figure in the academic world. He knew his first-year students by name. Naturally, he remembered their exam marks. And when they came to see him to try and find out where they had gone wrong, he remembered their papers perfectly and was ready and able to show them what they needed to do to obtain an improved result. In short, for a man with an extraordinary number of academic publications and citations to his credit, in many ways he was an old-fashioned pedagogue who loved sharing his knowledge and his enthusiasms and was never happier than when his students did well. And on this basis, it gives me great pleasure to announce the winning schools in the second senior category, in the Senior Secondary Category Award. So the first is Matari Makawatu to Notable Quintile 2 School. The Derang Natla Notable Quintile 3 School. The Lornutzi Lesedi Secondary School, which is a notable Quintile 3 school. St. Stithians Boys College, 10th place, Gauteng. St. David's Marist College, 9th place, Gauteng. Horizon High School, 8th place, Gauteng. Sacred Heart College, 7th place, Gauteng. Yeshiva College, 6th place, Gauteng. King David Victory Park High, 5th place, Gauteng. Red Hill High School, 4th place, Gauteng. The Lycée de Kigali, 10th place overall. The Cornwall High School, 3rd place, Gauteng, 9th place overall. Star College, Durban, 8th place overall. GSN DBC, which is 7th place overall. King David High School, Linksfield, 2nd place, Gauteng, 6th place overall. The École de Sciences Biimana, which is 5th place overall. The Graceland International High School of Nigeria, 4th place overall. The Rondebosch Boys High School, 3rd place overall. St. John's College, 1st place, Gauteng, 2nd overall. And the Ambassadors College, Otta, 1st overall.
Great, congratulations. Well, firstly, thank you very, very much, Michael, for presenting on behalf of your late brother. It was hugely appreciated. And a big congratulations to the senior secondary school winners, and particularly to the Ambassadors College, which came first overall. We are going to move on to the undergrad prizes, and this is going to be presented by John Karev himself. He is the competition organizer of the Wits Maths competition, and if you have any questions, I'm sure you can Google stalk him and send off those questions as well. But John, over to you to present the winning schools, the undergrad section.
Thanks, Simon. So I should say about the winning schools that we don't make it an inter-university competition. We allow undergraduates to get together into groups of 5 to 7, and you still write the paper individually as individuals at schools do, but we let the kids do this at, add up their ranks and the winnings and join up with their friends and make teams. And we very much hope that they make interesting puns for team names. So thanks to all the teams that made interesting names. makes the competition a lot more fun to mark. Third place from Wits is the winning team. Not quite, guys. Very good. The Wizards from Kenyatta in Kenya, second place. And from Wits, again, the limit does not exist. You guys have absolutely no limits. First place as a team. And now there's some special awards for things which aren't quite schools, but really did do very well as teams. So either elite training centers, well, I guess that's the main one. So Phil's Math Club is wins a special prize. TAPS, University of Pretoria CM Corbett Center, special prize, and EMS from Bloemfontein wins a special prize. And now it's time for an intermission, and we'll have our local speaker, Professor Benjamin Rossman, who Simon will introduce.
Thanks very much, John, and once again, a huge congratulations to you for running this competition so well. Benjamin Rossman is going to be our local speaker. He is a full professor in the School of Computer Science and Applied Maths at the University of the Witwatersrand at Wits, and he runs the Robotics, Autonomous Intelligence, and Learning Laboratory. That's the RAIL laboratory that I mentioned a little bit earlier. And is the director of the National E-Science Postgraduate Teaching and Training Platform, which is called NEP TTP. I'm sure they call themselves something catchy. I'm sure he'll tell us that in a moment. His research interests focus primarily on reinforcement learning and decision-making in autonomous systems, and specifically on how learning can be accelerated through abstracting and generalizing knowledge gained from solving related problems. He's a founder and organizer of the Deep Learning in Daba Machine Learning Summer School, and which has a focus on strengthening African machine learning. He was the 2017 recipient of a Google Faculty Research Award in Machine Learning and the 2021 recipient of a Google Africa Research Award. And in 2020, he was made a senior member of the IEEE. Prof. Rossman, thank you very, very much for joining us.
Thanks so much, Simon. You can hear me all right?
Yeah, absolutely fine. We've got you.
Great. It's great to be here with you all. And yeah, it's amazing to hear about all the work you've all been doing. It's always inspiring and exciting to engage with the next generation of really smart people, particularly in the maths field. And so again, massive congratulations to you all. Let me just put up some slides. Can you guys see this? I'm going to assume yes, if no one objects. But yes, so the main thing is congratulations. I think you're all making excellent life decisions by following a path of maths and hopefully really enjoying it and clearly doing well at it. But, I'm sitting here as someone who is fundamentally an AI person, right? So why is this AI person sitting here and talking to you, the budding young mathematicians of the future? Well, this is something as, well, I'm an AI person, but sitting in a computer science department. But it turns out that maths drives all of artificial intelligence. So if you keep an eye on the news and, well, pretty much anywhere at the moment, you're going to hear all the time about all the exciting new things that artificial intelligence or machine learning or deep learning is doing in our daily lives and how it's starting to affect the world. And I want to tell you guys a little bit about how really this is all maths. And if this is the kind of thing that's exciting you, you're already on the right path. And now it's been spoken about earlier how there's so many exciting opportunities in tackling problems in pure maths or looking at problems in applied maths and even how this can affect climate change. But I want to show you how this really can turn into a broader toolbox that you can use to kind of think about anything. So really what we talk about these days when we think about artificial intelligence is what's called machine learning. And the challenge is, as a computer scientist, I want to be able to solve interesting problems, right? This is like, I think of computer science as really doing maths with a computer. And if I want to be able to solve a problem, I want to be able to write a program that can solve that problem. So, let's say I wanted to be able to look at a photo and tell if this is a cat or a dog. How would I do that? Well, it turns out that's quite difficult to that piece of code might be difficult to write. If you think about how you might, there's some lighting in the background. If you think about how you might go about specifying this, what is it that makes something a cat or a dog? Well, we might sit and try and figure out the rules. It's something that's got a certain kind of nose or certain kinds of ears, but how do we describe this if we're looking at an image? And this is difficult. So the approach we generally take in artificial intelligence is to, instead of trying to write the program, we can think, well, maybe it's easy for me to collect examples. And what I want is, instead of me figuring out the rules, maybe my machine can figure out the rules for me. And this process is what we call machine learning. But actually, at the core, all that machine learning really is optimization. Well, a little bit of mathematical modeling plus optimization, which is a key mathematical process. You do your calculus, you take a derivative, you set it equal to 0, and you try and solve for this. Obviously, there's interesting techniques along the way, but that's what's going on at the core. Right, so the machine learning problem, which again is at the heart of artificial intelligence, looks something like this. What we're trying to do is we're trying to learn functions. Right, you're all familiar with functions. We want a function that can take as input this picture of a cat, and the output could be a label that says this is a cat. Right, that's just a function like anything else in maths. But in this case, we actually want to learn that. We want to be able to learn how to get that mapping, that function, from the picture to the label or the text. And the way we do this is through a process called training. We train our models. They learn. We give them examples where we know what the correct answer would be. We know that this one's a cat, this one's a dog. And we use that to train the model. And what do we mean when we talk about training? That's that optimization I was talking about. So why do we do this? Well, we want to be able to predict the labels for new images. So now if I go out and I see a cat or a dog that I've never seen before, I should be able to tell what the answer is based on the ones that I've seen before. Well, what is this? Let's say we took a little example. Then instead of pictures of cats and dogs, we looked at two other features of our cats and dogs. One might be the size of the animal, and the other might be how domesticated our animal is. Wait, I'm seeing something that we can't see the slides. Can you see the slides? Anyone? John? Simon? Oh, that looks better. Cool. Sorry about that, everyone. Let's see if I can just rewind a little bit. Yeah, okay. So, well, nothing really needed pictures before. Okay, so let's look at this idea if we're going to try and classify animals based on their size and how domesticated they are. Right, so we might get something like this. We could have a little kind of graphical setup here where we've got our two variables, how domesticated an animal is and what its size is. And we could have a couple examples that we've seen before. Remember, what I've been trying to tell you about is we want to learn how to tell the difference between the two things. So you can imagine that this cat is like at this point here, this domesticated and this size and so on. And what we want is, if we're trying to tell the difference between them, maybe we want to fit a straight line between the set of all dogs and the set of all cats. And the process of machine learning is that as we get more and more data, we should be able to get a better fit of this line to the data. So having seen a few examples, now if I've got a new point that I want to query, I might say, what is an animal that's kind of a little bit domesticated and not too big? Well, maybe that's, if you look at this picture, if that lies below the line, we can maybe tell that it's a cat. So what have we done here? We chose a model. What is the model? The model was a straight line. And we said, if you're on one side of the straight line, you're a dog, on the other side, you're a cat. How did we fit this line to our data? Well, we did optimization. What did we do that optimization on? Well, if the straight line is y equals mx plus c, this means we optimize the m and the c to get a good fit to our data. So this is really telling us something about the geometry of our problem. So again, at the core, we're looking at mathematical processes to try and tell the difference between cats and dogs. Okay, but in general, this is more complicated, and we base a lot of our modern models on the idea of the neuron in the brain. So this is a brain cell, and what's cool is in your brain, you've got like 100 billion neurons, which are your brain cells, and something like a quadrillion synapses, which are the connections between the brain cells. And it turns out they learn in a very similar way to what I was just describing. So the process looks something like this. You've got a set of neurons we can see on the left here, and neurons send signals to each other. They send little bursts of electrical activity, and they send these to the other neurons they're connected to. So in this little picture here, we might have these 6 ones that can send a signal to the one on the right. Now, the signals they send depend on how strong the connections are. Some of these connections can be positive, and some can be negative. So the positive ones make the one on the right more likely to send out its own signal, and the negative ones make it less likely. These are the strength of the connections or the strengths of the synapses. Right? And this is the way the brain works. It sends signals around between these billions and billions of neurons, and as it does this, the strength of the connections changes, and that's what we call learning in the brain. But this is actually just a simplified model that I've given you here. Right? There's actually all sorts of chemical and biological things going on. Now, if I take this picture, we can turn it into a mathematical model. Right? We could just treat all of those neurons instead as a tiny little computational unit. Or actually, in practice, we can treat it as essentially a little number that's carrying some information. And these neurons are going to then pass some information around from kind of one part to another. And we're going to do this based on the strengths of these connections. So I might have some properties here which correspond to things like the size or level of domestication of my animal. I could have some sort of this synaptic strength, the importance of each feature, and based on that, I'm going to make a prediction. Now, again, this is just a mathematical model of this process that I was describing in the brain. And actually, these importances, these connection strengths are the important things. And these we just treat as matrices. So a matrix where every number in the matrix just tells you how important one of these neurons is to the next one. So it works like this. Let's say I had, say, a dog I was encoding. I could put in all the properties that I care about. And then I multiply it by these importances. I pass it through another function over here, and it makes a prediction. So it might tell me that this is a dog. So if it says that it's a dog, and this is correct, then we don't need to do anything. Now, we might give it another example. We might say, here's a cat. We encode in the properties. Again, we multiply it by these strengths. We use a little nonlinear function, and that will give us a prediction. But now it might tell me that it thinks this is a dog. Now, I know that this was actually a cat, so I could say, no, that's a bad computer. This should be a cat. And to actually be a cat, what we're going to do is change these connections so that it's less likely to make that error. And what does it mean? This is where the optimization is coming in. So effectively, we're using a bit of linear algebra. We're going to use a bit of calculus. And we figure out how to change these connections so that it's less likely to make that same mistake again. And if it's less likely to make that mistake again, that's what we call learning. So this is the process really of what's going on. And turns out this is the mechanism that we use to really drive a lot of what happens in machine learning. Now, this is used all over the place. And to give you some examples, this really simple technique with a few extra bells and whistles attached to it has been able to do amazing things. So for example, here's some instances of the system being given images it's never seen before, and it's making some predictions. So for example, the second one, it predicts it's a container ship. The fourth one, it's predicting this is a leopard. Sometimes it makes mistakes. So, this one over here, it predicted was a Dalmatian, but actually someone had decided this was a cherry. So, this is pretty great. And again, this is all learned by this idea of doing optimization on these kind of mathematical models that we've set up that emulate something about what the brain is doing. We can do all sorts of interesting things, and I've just picked out a couple examples here to show you. I've shown you how we can work with images. We can do very similar things with text as well, and we can even combine them. So using these kinds of models, we can build, build programs or build these neural networks, as we call them, that can, given an image, generate a caption for it automatically. So we could give it this image it's never seen before, pass it through our models, and it could produce the text that says, a group of people shopping at an outdoor market, there are many vegetables at the fruit stand. Now, again, this is coming up with clever ways to do this optimization based on these models. Again, at the core, this is just some linear algebra working with vectors and matrices. This is different kinds of optimization based on calculus. And all of this is really coming together to be able to build these models that can learn. And then, there's all sorts of crazy fun stuff that people have been doing. What's been happening recently is this idea of models that we can give it text and it draws images. So there's a few of these things now. I could give it a prompt that says, draw me an armchair in the shape of an avocado. And it could draw you these kinds of pictures. So it's kind of almost expressing creativity. But again, at the core, we're using similar kinds of mathematical processes that's driving all of these interesting technologies. We could ask it to generate a photo of a puppy wearing a black suit and a bow tie. These are images that aren't online. It's generating these itself. Or even something crazy like Batman and Godzilla in a spa, right? So these are all interesting applications of the same fundamental concepts mathematically. We can even take this a step further, and this is the kind of thing that I work on with my group. We can look at how did we get machines to make decisions. So we could have a machine that lives in some environment. It could be a factory, it could be a browser sitting on your computer, and it's got to make decisions, right? So we want it to be able to take actions, which is computing the best next thing to do. That's a kind of optimization. We want it to learn how the environment changes over time if I do certain things. And we've already looked at how learning is just one of these kinds of problems. And we might want to learn what is desirable. When do good or bad things happen? Well, the same kind of techniques apply for these kinds of problems. And there's been a lot of interesting work done in this space. So for example, in the last, say, almost 10 years, people have been looking at trying to apply these techniques to video games, for example. So what you could do is we could take a case where we have this algorithm. It doesn't know anything about the problem, and it's going to learn as it interacts with the problem. So it could move around, it could gather data, it could learn from the data in kind of processes like I've described before. And over time, it can go from what you see here, which is being terrible at playing this game, right? It's trying to move that little paddle around at the bottom to bounce the ball to hit those colored blocks. And over time, it can get better and better at playing this game, again, through this learning process, which works using the kinds of concepts I've been talking about. And you can see here that over time, it's learned to play the game better, right? And this is really about understanding what's happening in the environment. It's about learning what the right action to do is. And at the core, again, all of this is just mathematical modeling and doing some optimization on top of that. And in fact, with these kinds of systems, what's quite fun is if you leave them learning over time, they learn how to kind of hack the game a little bit. So you can learn these really good strategies that maybe a really good player of the game might learn of kind of playing the game like this. So you can tunnel the ball up the side and it gets really good at it. And these same kinds of ideas have been used in really complicated settings. This is a strategic video game called StarCraft, where you have to manage, you play as one of these alien races, and you have to manage resources and build mines and build bases and economies and train different kinds of units to fight your opponents, but defend your own base and explore alien worlds and so on. And even these kinds of things, we're able to build these systems that can really process the pixels that it sees on the screen to make these decisions. At its heart, all of this is the same kinds of technologies again and again. We do this kind of stuff in our lab as well. So I wanted to just give you a couple examples that I think are quite cool. So here's where we've got this little simulated robot that we've had it learn how to do different things. So in this office environment, it's learned to run around and it picks up mail if there's anything in the mail room, and maybe it will take coffee to people in the office that need coffee. And then it might wander around and patrol the environment and avoid fragile decorations and so on, right? This is, again, the kind of example of something that's learned how to interact with its environment based to some extent on the way we work as humans. Again, at its core, all of this is mathematics. We do some fun stuff with robots as well, because, you know, the kind of applied version of maths is applied maths, and the applied version of that is computer science, and the applied version of that might be robotics. So we can look at examples of figuring out how to get our robots to drive around different environments or move blocks around to solve different kinds of problems. And again, these are the kinds of things, these are examples from my lab at Wits of how we're using these techniques to get robots to do interesting things. But we, don't just play with robots. We look at all sorts of real-world problems using machine learning and AI as well. So, for example, you could look at how robots and humans might work alongside each other in a factory. Maybe here we've got a human that's struggling to solve some sort of problem, and if the robot can try and learn when is the human struggling, can I recognize what's going on? Maybe I can help the human with the task they're trying to solve. We've done all sorts of other interesting things with robots. We can apply these techniques to soccer. So we've got a team of robot soccer players. They're in simulation, but again, they're trying to do this learning to be able to solve these problems. We've got to think about issues when we deal with robots around geometry. Where are the arms? Where are the legs? What is the correct way to move? All of these aspects come into these problems. And then we try and look at how to apply these to other real-world problems. We've looked at, can we improve the growth of crops using different kinds of machine learning? Can we improve the way we think about medicine, whether it's being able to diagnose problems with X-rays or blood cells? We've looked at problems in trying to reduce the amount of water hyacinth, which is an invasive weed that can grow on dams. And we can do this by trying to figure out where it is from satellite images, which is one kind of machine learning problem. We can do this, we can look at trying to reduce and control the water hyacinth, which is another kind of machine learning problem. We've looked at questions in education. And here we can ask the learning problems of, can you maybe predict when a student needs help or when they're struggling with something, or even can you predict what the best content to show a student might be so they can do better and achieve their learning tasks better. And even looking at questions around using robots to explore caves and help us do science. These are all the kinds of questions that you can look at with these types of techniques. So really what I want to encourage you is to think about maths. I think most of you would enjoy maths for the sake of maths, but it really opens a whole lot of doors to you. And this is just one field. I've just been talking about machine learning, and I'm pretty sure anyone in any science or any field of engineering, and even other fields, the social sciences, people more and more at their core use mathematical techniques to look at interesting problems, solve interesting problems, and really go about trying to build a better world. So with that, I want to thank you for listening. These are some of the wonderful people that get to work with us at Wits. But I hope you all just grow your mathematical passion. I hope you find new, exciting opportunities to keep using it and to keep asking questions and helping the world. Thanks, everyone.
Thank you very, very much, Benjamin. Can we? Oh, well, he's disappeared already. But thanks so much. Absolutely fascinating, and it's the world of AI is going to be such an interesting place for mathematicians to work again, to work in the coming years. It's a very, very exciting time indeed to be interested in maths. Right, let's move on to our individual awards. And the first that we're going to be looking at is the Middle Primary Awards. And these are going to be presented by Prof. Margaret Archibald. She is the Associate Professor of Mathematics, and her research interests are in combinatorics, as well as enumerative combinatorics and discrete maths. She's NRF rated. She has been for a while, since 2011. Works as a researcher and a lecturer at Wits and at UCT over the past 20 years. Has supervised a number of postgrads and has published over 30 journal articles in ISI journals. Prof. Archibald, thank you very, very much for joining us, and I'll let you take the Middle Primary away.
Thanks very much. So for Middle Primary, we start off with a notable Quintile 2 learner from Chokwe Primary School, and it's Kay Semenya. Congratulations to you. Another notable Quintile 3 learner from Tembali Kazulu Primary School is A. Mabaso. All right, so moving on to best proofs overall, 10th, and best proofs in Gauteng was S. Smith. from the Advanced Learning Centre. From Rustenburg Girls Junior School in the Cape, 10th place overall, is M. Wallace. Congratulations. So Law School Henops Park is 9th place overall, 9th place Gauteng, M. McPhail. And then J.Y. Chen from Red Hill was placed 8th overall and 8th in Gauteng. Nice symmetry going there. Okay, R. Bester from Law School Henops Park is also 7th place overall and 7th place Gauteng. I have a feeling this is going to continue. I like spotting patterns, that's what I do. Okay, Q Zhang from Red Hill was 6th overall and 6th in Gauteng. And E Ning from Red Hill also was 5th place overall and 5th place in Gauteng. All right, M Tian from Red Hill is 4th place overall, 4th place in Gauteng. And up to the podiums now, also from Red Hill, we have A Sun, who is 3rd place overall and in Gauteng. In 2nd place overall and in Gauteng, also from Red Hill, was In Ntuli. And the winner for the middle primary was Q Zhang from Sherry Home School. 1st place, top girl overall, 1st place, and top girl Gauteng. Congratulations to all of you. And we hope to see you again next year.
Thank you so much, Margaret, and congratulations to those folks who won the awards in the middle primaries. We're going to move on to upper primary, and our presenter there is Prof. Betsy Yonk. She's a professor in the Wits School of Mathematics, so much, Margaret, former head of school, and she is the co-founder of the WMC competition, the Wits Maths competition. Betsy, thanks so much for joining us. Prof. Young, you are on mute. Here we go. Former school, and she is the co-founder of the WMC competition, the Wits Maths competition. Joining us.
Thank you very much, Simon.
Prof. Young, you are on mute. Here we go. Former school, and she is the co-founder of the WMC.
Our notable quintile 2 learner, B. Machaki,
you are on mute.
Primary.
And she is the founder of the WMC.
Okay, our notable quintile 2 learner, B. Machaki, Robotics Primary, notable quintile 2 learner, SHY, Bezeni Kumai. Again, our 9th place, Gauteng, son of St. John's Prep. Then the 9th place, Gauteng, and Johnson, Trinity House, Randburg.
Hi, Prof. Okay, so we've got a bit of a problem there. I don't know if you've got some headphones that you can use so that we don't get that howl round. So I'm going to reread these, and perhaps Prof can just come on at the end if she's able to get some headphones. Right, so the winning learners for the upper primary, the notable quintile learner, the first one was B. Majake from Boitakong Primary. Then S. Klatswayo, another notable quintile 2 learner from Mbazene Combined School. And then from St. John's Place, 9th place in Gauteng, F. Sadonik. Joint 9th place in Gauteng, A. Johnson from Trinity House, Rand Park Ridge. Again from St. John's, 7th place in Gauteng, J. Lee. And that then brings us through to a 6th place for Gauteng from Red Hill, M. Chen. 5th place in Gauteng and 10th overall, S. von Gottenberg Cohen. 9th overall, and from Sweet Valley Primary, L. Brown. 4th place in Gauteng and 8th overall from Law School Tigerpoort, J. H. Jordan. And then 7th place overall from Sweet Valley Primary, S. Swart. 3rd place in Gauteng and 6th overall, I. Morris from King David Victory Park. Second place and best lady in Gauteng. 5th overall, R. Moultrie from Auckland Park Preparatory School, where my daughter attended in her grade 7 year. From Somerset House, 4th place overall, J. Coolen. Then 3rd place overall, also from Somerset House, O. Castleton. 1st place and best proofs in Gauteng, and 2nd overall from Homeschool Schoolman, it is Al Schoolman. And 1st and best proofs overall from Jay Skiba from the International School of Cape Town. Thank you very, very much. Congratulations, rather, to all of those winners in the upper primary category, and particularly to Master Skiba from the International School of Cape Town. Right, we'll be moving on to the winners of junior secondary section, and this is the John Knopfmacher Prize, and it is to be presented by Arnold Knopfmacher, who is the professor of mathematics, whose research interests are in combinatorics, and is the son of the late Professor John Knopfmacher. Arnold, over to you.
Good evening. I would just like to say a few words about my late father. He was a leading South African research mathematician throughout his career, right up till the time of his retirement. And in addition, he served as the head of School of Mathematics at Wits for a period of 9 years. I guess I'm now ready to announce the winning learners. From Mbuzeni Combined, notable quintile 2 learner, Gina Kozi. Also from Mbuzeni Combined, notable quintile 2 learner, T. Rakalakani. And again, Mbuzeni Combined, notable quintile 2 learner, T. Kuneni. From Hura School, Hopetown, notable quintile 4 learner, A. Victor. From Yeshiva College, 10th place Gauteng, Y. Krasner. From Woodhill College, 9th place Gauteng, S. Ravji. From Currow Park Dean, 8th place Gauteng, N. Mashia. From St. John's College, 7th place Gauteng, O. Bulliard. From St. John's College, 6th place Gauteng, E. Han. From Red Hill School, 5th place Gauteng, Y. Zan. From British International Prep, 4th and best lady Gauteng, as well as best lady overall, K. Chana. From Trinity House, 3rd place and best proofs in Gauteng, C. Johnson. From Wilson Homeschool, 10th place overall, D. Walton. From Rondebosch Boys, 9th place overall, E. Williams. From the Ambassadors College, 8th place overall, D. Oyerindi. From Graceland College, 7th place overall, A. Adoga. From Trinity House, Rand Park Ridge, 2nd place Gauteng and 6th place overall, J. Monchui. From SA College High School, 5th place overall, N. Rousseau. From Welkin International School, 4th place and best proofs overall, I. Olajidi. From Rondebosch Boys High, 3rd place overall, S. Steer. From King David Linksfield, 2nd overall and also 1st in Gauteng, N. Greenblatt. From Phil's Math Club, 1st overall, Y. Kim.
Thank you very, very much, Arnold, and a big congratulations to the winners of the junior secondary category. And I'm surprised as you are to be joined by John. Do you have an announcement?
Yeah. So the next two awards are named after Professor James Ridley and Professor Peter Sarnak, both from, well, James was at Wits before retiring, and Peter was is now Princeton and is one of his best-known students. And I'm just going to say a few things to introduce both of them. I'm sure James will say a few nice things about Peter too, but I'm going to say some about James. So, I mean, James really is, I think, quite possibly the best mathematics teacher I've ever seen. Every time he gives a talk, I kind of walk away going, oh, that's what I'm supposed to be doing. Oh, okay, I'm going to go home and try to do better. I mean, I still remember things he taught me when I was in high school and how the proof went and what the trick was. It's really pretty great. About once a year, we get him to come and give an extra talk at the Sean Corbett Center. Shameless plug for that. And I'm going to say a couple of nice things about Peter too. So he's, sort of universally acknowledged as one of the best research mathematicians in the world. And when I've come into contact with American mathematicians, and this happened 5, 6, 7 times, I'd sort of say something and be told, oh, you're South African. Usually by someone who was in their own right quite famous. And then they would proceed to tell me about how they knew Peter. Well, you're from Wits. And they say, I was a grad student when Peter was a postdoc. I was a postdoc when Peter was a professor somewhere. And at the time I hadn't met Peter. So I just kind of went, oh, yes, I've heard of him. And when I finally did get to meet him, in really exactly the same tone, he sort of said to me, well, oh, you're from Wits. That's very nice. Do you know James Ridley? And yeah, without any further ado, please welcome James Ridley.
Well, thank you, John. That's very kind of you, very kind words. But certainly, Peter Sarnak, I'll say a little bit more about him when it's his turn. It certainly was a privilege to teach him, and I've always loved teaching as well as doing my own research. And so I'm very happy to be able to participate in a very small way in this evening's proceedings. And so these are the senior secondary winners. Firstly, a notable quintile 3 learner from school Dirankanatla, T. Pizzo. And also from Dirankanatla, another notable quintile 3 learner, X. Tengwa. And from Hoërskool Hopetown, notable quintile 4 learner, J.H. Fourie. And from De La Salle, best proofs in Gauteng, K. Edmonds. And from Woodlands International College, the best proofs also in Gauteng, S. Lin. From King David Linksfield High School, 10th place in Gauteng, Y. Wayner. From Cornwall Hill College, 9th place in Gauteng, D. Reddy. From Rodin, somebody I know, 8th place in Gauteng, Yufei Gao. From King David Linksfield, 7th place and best proofs in Gauteng, A. Perlman. From St. John's College, 6th place in Gauteng, A. Tefur. From Cornwall Hill College, 5th place and best proofs in Gauteng, L. Andrews. From St. John's College, 4th place and best proofs in Gauteng, C. van Lochrenberg. From Witziangoba, 3rd place and best lady Gauteng, J. Espos. From St. John's College, somebody else I know. Second place and best proofs in Gauteng, Jonathan Stagman. And also from St. John's College, first place in Gauteng, A. Clark. From Westerford High School, now we move to the Cape, 10th place overall, A. Sinclair Smith. From Phil's Math Club, 9th place overall, A. Conradi. From Paarl Valley High School, 8th place overall, B. Klein. From JNS High School, 7th place overall, B. van der Westhuizen. From the Ambassadors College, 6th place overall, M. Akinola. From Rondebosch Boys, 5th place overall, J. de Villiers. From Phil's Maths Club, 4th place and best lady, J. Rue. Again from Paarl Valley High School, 3rd place overall, J. Slater. Another one from Phil's Math Club, 2nd place overall, M. Kim. From Sachs, from South African College High School, 1st place and best proofs overall, E. Rousseau. So congratulations to you all. You've really done wonderfully well. It's a privilege to be able to know about all that you've done. And now it's the Peter Sarnak Prize, the undergraduate prize. So I will say a few things about Peter. It was my privilege to teach him in his honors year at Wits. It's getting on for nearly 50 years ago. And he went from Wits to Stanford, near San Francisco, where he did his PhD under Paul Cohen, who proved the continuum, independence of the continuum hypothesis, among other things. And the one thing that I've always remembered that Peter's always been very willing to acknowledge is that the undergraduate teaching that he got at Wits was equal to, and in many cases better than, the teaching of his contemporaries at Stanford, which is, as you all know, one of the top universities in the States. So that's something that he has always been willing to admit to everyone, and that Wits can rightly be proud of. The other thing, Peter Sarnak, he is at Princeton. He has been there most of his working life, though he has had time at Stanford and also Columbia, I think it was. But he was one of the few people who spoke to Andrew Wiles when Andrew Wiles was busy proving. First he made a mistake, but then he did get it right a couple of years later when he was proving Fermat's last theorem and really turning it into a theorem instead of just a conjecture. So that's one thing. And another thing, I've very recently read a very interesting book that you might like to dip into. Some of it's maybe a bit difficult, but you can always skim over them. A very good book called The Music of the Primes by Marcus de Sotoy. Some of you may have read it already. But there are a few references to Peter there. And there's one that really amused me when he talks about how Peter's South African accent, which he hasn't lost in nearly 50 years in the States, how his South African accent would ring across the tea room at Princeton when he was speaking to someone. So that's also a nice thing about Peter, that he's proud of being a South African. So let's have our winners. Our top lady in Gauteng from Wits is B. Zita. Our 10th place in Gauteng from Tukkies is G. Tron. Also from Tukkies, 9th place in Gauteng, S. Nuruddin. From Wits, an 8th place in Gauteng. Obviously, we're alternating here, almost. L. Mkwanazi. And Wits, 7th place in Gauteng, J.S. Huang. Another Wits, 6th place in Gauteng, C. Abrahams. Another Witsi, 5th place in Gauteng, N. Philip. Another Witsi, 4th place in Gauteng, P. Chikasa. And now a Taki again from Pretoria, 3rd place and best proofs in Gauteng, C. the Nation or Nation. 2nd place in Gauteng from Wits, M. U. Mula. And from Stellenbosch, 10th place and best lady overall, K. Porro. 9th place overall and 1st place in Gauteng, M. Dreekmeijer. From Stellenbosch, 8th place overall, J. Waite. From GS St. Paul de Taizo, I wish I knew where that was, 7th place overall, J. Munezero. From Stellenbosch, 5th overall, A. Williams. From Stellenbosch, also 5th, but best proofs overall, N. Sander. From the Ambassadors College, OTA, I wish I knew what that was, where that was. The Ambassadors College, 4th place overall, O. Emmanuel. And from UCT, 3rd place overall, J. Boertus. And again from UCT, 2nd place overall, J. Huig. And the overall winner from Stellenbosch, so Marties wins again, 1st place overall is F. Steenkamp. So congratulations again to all of you undergraduates, and I hope that all of you will take Peter Sarnak as your role model and try and emulate him to the best of your ability. Congratulations and goodbye.
Thank you, Prof. Ridley. I believe that GS St. Paul is in Rwanda. When Peter's complimentary about the education he received at Wits, normally he's complimentary about the education he received from James Ridley. Fortunately, Wits is full of people who were taught by James, so it's still a great place. Those are all the awards, so congrats to everyone. And I think it's time to give some final thanks before we leave you for the year. So firstly, thanks to everyone who helped set. There were just too many to name: Betsy Yonk, Graham Evans, Phil Labaskatni, Evans Neyman, Kellen Kotson, Mwande Konya, and Jacqueline Fenter. I'm sure I'm missing out many more. I'm very sorry. Our regional coordinators, Andrew Obers, Matthew Smasole, Phil Labaskatni again, Jessica Verbrett, Graham Evans. Thank you guys. We really could not do this without you. Of course, a big thanks to all the teachers and who sit after school and give out this extra exam when they have a million other things that they'd rather be doing, I'm sure. Thank you guys. We really appreciate the fact that you do this for your students and learners. Thank you to Sharp and Wits for sponsoring the competition. And yeah, see you guys next year.